Quantum physics. Much of the modern science depends on it. It is the best model we have right now to describe the subatomic world. The behavior of electron, proton, neutron, photon, or light can be described really accurately by quantum physics. As these particles are some of the building blocks of matter and energy, understanding their behavior makes us understand how nature works. Some of the technological applications of quantum physics are solid-state physics or semiconductor physics. Entire electronic industry depends upon it. MRI machine, laser technology, nuclear physics, etc. All of this started with a catastrophe known as ultraviolet catastrophe, which physicists encountered while trying to explain black body radiation spectrum by classical physics. Throughout the video, I have discussed how physicists came up with a solution for this catastrophe. The radiation spectrum of black body baffled physicists all over the world in late 1800 to 1900. Gustav Robert Kirchhoff formally defined a black body and described some of its properties in 1860. Physicists tried to describe the black body radiation spectrum mathematically by the law of thermodynamics and electromagnetism. But all their attempts failed, as none of the derived formula could predict the spectrum as observed from the experimental data. Some of the earlier attempts are Rayleigh-Jeans law and Wien's approximation, but they only approximate the actual underlying formula for black body radiation spectrum for low frequency and high frequency respectively. Finally, Max Planck derived the mathematical expression for radiation spectrum exactly in his monumental paper published in 1900. In the process, he started a completely new branch of physics known as quantum physics. His work on black body radiation became the bedrock for the later development of quantum physics, which is the basis of much of the technological advancement of modern science. The way Planck solved this problem was by considering energy to be discrete. Now, why did he do that? Did he one day just wake up from his sleep and randomly say, you know what, let's make energy discrete? And his guess just conveniently turned out to be correct? No, that's definitely not what happened here. Energy was considered continuous for 200 years before him, and he himself believed it to be true. Then there has to be a reason and evidence so compelling that forced him to believe that energy has to be discrete or quantized. And there really was an evidence like that. In this video, we are going to rediscover that evidence, but for that we really need to go through some serious math. But don't be disappointed, because at the end of the video you will finally understand the real reason behind the quantization of energy. So all these complicated maths are worth it. Planck basically borrowed a trick which was used by Ludwig Edward Boltzmann in his monumental paper of 1877, where he basically invented the big ideas of statistical mechanics. In this video, our objective will be to derive the mathematical form of black body radiation spectrum from scratch. We will go through 4 steps for fully understanding the derivation. Now, before we start the discussion, let's make a quick review of some important concepts. First, what is radiation? It is nothing but the propagation of electromagnetic wave through vacuum. We all know from Maxwell's equation that when a charged particle wiggles or accelerates, it generates EM wave and that travels from the source to everywhere around at the speed of light. Since matter is made of atom, which is made of charged particles like electron and proton, they are not stationary. They are always vibrating and creating electromagnetic wave which carries energy. This is radiation. Second, what is black body? We have all seen when we keep heating an iron bar or any metal or solid material, it starts to glow. First it is red, then orange, then yellow, And if we can make it really hot, then white. It is an example of black body. It's any kind of body that is capable of absorbing electromagnetic wave of all spectrum and radiating electromagnetic wave of all spectrum. Sun is a good example of black body, but in real life, objects don't really absorb electromagnetic wave of all spectrum and radiate electromagnetic wave of all spectrum. So they are not ideal black body. In this video, we are going to study ideal black body, because if we know how an ideal black body works, we can adjust it to fit the real world black body. It was clear from the experiment that the intensity of black body radiation differs for different frequency of electromagnetic wave. In fact, the graphical relation of intensity and frequency of electromagnetic wave looks as shown in the figure. This graph is known as the black body radiation spectrum. Since before 1900, physicists considered physics to be complete, they should be able to derive the same relation for intensity and frequency as shown in the graph from classical physics using only the laws of thermodynamics and electromagnetism. That's exactly what Rayleigh and Jean, two British physicists, tried to do. They tried to derive the black body radiation spectrum from the law of thermodynamics and electromagnetism, and it failed terribly. So we start from Rayleigh-Jean's law. John William Strutt, or title Third Baron Rayleigh, known as Lord Rayleigh, and Sir James Hopwood Jeans were one of the first few physicists who tried to mathematically model the black body radiation. They published their finding in a paper in the middle of 1900. The law they came up with is known as Rayleigh-Jean's law. Here is how they deduced the law. Consider a cubic cavity with length as shown in the figure. It's a metallic cavity. The cavity walls continuously emit electromagnetic radiation in all directions. Since these are metallic walls, at the surface of the wall, the intensity of electromagnetic wave is always zero, and the wave inside creates a standing wave, and they always have a node at the surface of the wall. To figure out the total energy radiated by the walls as electromagnetic wave, first we need to calculate the total number of standing waves formed inside the cavity and multiply it with its energy. Now to calculate the number of standing waves inside the cavity, first we need to figure out the nodes inside the cavity. The condition is that at the cavity wall, electromagnetic wave is zero. The intensity of electromagnetic wave is zero. Since it's a metallic wall, there can be no resultant electric or magnetic field beneath the metallic surface. That means any wave with half wavelength equal to A by n, where n is an integer, can fit inside the cavity. The walls create electromagnetic wave of all frequency, but we need to show how many waves of frequency nu to nu plus d nu can fit inside. Let's derive the relation between modes and frequency first. We have seen that any wave having a half wavelength A by n can fit inside the cavity. That means lambda by 2 equal to n by n, where lambda is the wavelength of the wave. Hence n equal to 2 nu by c, where c is the speed of light and nu is the frequency of the wave, and a is the length of the cavity. In fact, the wave can travel toward any direction inside the cavity. So in general case, consider the figure shown here. Here we can see a plane electromagnetic wave traveling toward an arbitrary direction with wavelength lambda. I will leave it as an exercise for you to show that this relation is true. And since 2a by lambda x equal to nx, where nx equal to 1, 2, 3, and the same is true for ny and z, we can write this equation And let's consider nx square plus ny square plus nz square equal to n square. Then we get n equal to 2a by lambda and lambda equal to c by nu. So we can write n equal to 2a nu by c, which is true in general. The relation between the modes looks exactly the same as Cartesian coordinate. So let's imagine a 3D Cartesian coordinate system with x, y, and z replaced by nx, ny, and nz respectively. Now consider the figure shown here. In the figure, I show a 2D frequency coordinate with nx and ny. We need to calculate the frequency modes between nu and nu plus d nu. As we can divide the dimension of the cavity into as many equal pieces as we like, we can see that the number of modes between nu to nu plus d nu is equal to the area between the two circles. Now consider the same situation in 3D. In this case, the number of modes is equal to the volume between the two spheres with radius nu and nu plus d nu. The volume between them can be shown to be this. As the same number of wave is produced in opposite wall, the total number of standing waves inside the cavity is this. We just need to multiply the whole expression by 2. Now we just need to calculate the average energy contained in each of the waves with frequency between nu and nu plus d nu. To figure that out, we need to realize that electromagnetic waves are produced by harmonic Hertzian oscillators. They all have different kinetic energy and potential energy, which is a mathematical form of half mv square and half kx square respectively. If we consider that the energy associated with each of the Hertzian oscillator has an energy distribution which follows Boltzmann distribution, then the kinetic energy with each of the Hertzian oscillator can be calculated as this, where P epsilon is the probability of finding a wave having energy epsilon. Later I am going to derive this law, so believe it to be true for now. Then the average kinetic energy associated with each of the Hertzian oscillators with velocity v can be calculated as this, where epsilon bar is the average kinetic energy of each of the Hertzian oscillator. If we calculate it, we get half kVt. If we do the same for potential energy, we get the same average energy. Then the total average energy the Hertzian oscillator has is kVt. Now we know the average energy associated with each of the Hertzian oscillator. We know that average energy associated with each of the waves with frequency between the range nu to nu plus d nu, which is kVt. We multiply it with the previous equation and get the energy associated with each of the waves. To get the energy density, we divide the equation above by volume V, which is AQ, and get the energy density distribution for the wave of frequency range nu to nu plus d nu as shown here. This equation is known as Rayleigh-Jeans law after John William Strutt and Sir James Hopwood Jeans. They published this result in June 1900, and we immediately see a problem with this law. According to this law, at high frequency, the amount of radiation emitted by black body would be infinite, which is absurd. Around the same time, Henrik Rubens and his collaborator Ernst F. N. Nichols conducted meticulous experiment to figure out the energy distribution function with respect to frequency, and they found a graph shown here. As you can see, there is a huge discrepancy with the classical result and experimental result. Although in the low frequency region, the classical result approximates the experimental result pretty closely, but in the ultraviolet range of the frequency, the results don't match at all. Later, it was known to be ultraviolet catastrophe. Now, as we have seen, if we strictly follow the classical theory of thermodynamics, we run into catastrophe. So instead, let's try to figure out some of the properties of the experimental graph and try to approximate the radiation spectrum and see how far we can apply classical laws of thermodynamics to derive the exact curve. We will determine where exactly classical law fails and apply a new law to fix it. That's exactly what German physicist Wilhelm Karl Werner Otto Fritz Franz Wien did in his 1896 seminal. To bring out some of the properties of the graph, we do a simple transformation first. We increase the length of the cavity in x, y, and z direction and see how the frequency spectrum changes. We expand the cavity such that L becomes L prime. The process is adiabatic, radiation stays in equilibrium. Let's define a factor alpha equal to L by L prime. Since frequency is nu, which is proportional to 1 by L, we see that nu prime is equal to alpha nu. Then volume scaling is V prime equal to V by alpha cube. Now to see how the temperature transforms because of the transformation of the dimension of the cavity, we need to do some math. We know that temperature and internal energy are related by Stephen's law. Capital U is proportional to T to the power 4, or the fourth power of the temperature. So let's examine the relation between the internal energy and volume of the cavity first. It is clear to us that radiation exerts pressure. Imagine electromagnetic wave falling onto a surface of cavity and it is absorbed. What is the force that is applied on the wall? It is equal to the change of momentum divided by time. Let's assume that it takes delta t time for the wave to go from one wall to another inside the cavity, and then the light is absorbed by the other wall as it's a black body, and the momentum is also absorbed. So the change in momentum is delta p. Then the force applied on the wall is F equal to delta p by delta t. It is a well-known fact in electromagnetism that momentum of electromagnetic wave is P equal to E by C, where E is the energy of the electromagnetic wave and C is the speed of light. We also know that delta T is equal to L by C. L is the length of the cavity, C is speed of light. Putting all of this in F, we get F equal to E by L. Then forces applied in the x, y, and z direction are Fx equal to Ex by L, Fy equal to Ey by L, and Fz equal to Ez by L. Then the pressure exerted on each of the wall is as shown. We just need to divide force on that wall with its area, which is L square. Then you get these expressions. Since pressure is the same in all directions, so we can say Px equal to Py equal to Pz equal to P. So by adding all of them, we get this expression, and hence P equal to 1/3 capital U by V. We have established a relation between pressure and internal energy. Now let's apply the first law of thermodynamics. dq equal to du plus P dV. Since the process is adiabatic, we can say dq is equal to 0. By substituting the value of P from the previous equation, we get this relation. And ultimately we see that small u, which is the energy density inside the cavity, is proportional to 1 by L to the power 4. Small u is just the energy density. You need to divide the total energy inside the cavity, which is capital U, by its volume. Then we get small u. From Stephen's law, we know that for small u is proportional to the fourth power of temperature. Hence we can say T to the power 4 is inversely proportional to L to the power 4. Then T is proportional to 1 by L and T prime is equal to alpha T. Now we know that energy density function small u is a function of the frequency nu and temperature T. We can change the dimension of the cavity, nu and T changes. How does it affect small u? To determine that, we need to make a reasonable assumption first. which is even if we change the dimension of the cavity, the total amount of energy it radiates does not change, since we are not changing the number of Hertzian oscillator inside the cavity. That means energy associated with each of the frequency strip of the frequency spectrum does not change even if we transform nu to nu prime and temperature T to T prime, as we can see in the figure. So we can write this and figure out a relationship between the transformation. This is an important property of the energy density function. According to this property, the function can be written in the following form. I will leave it as an exercise for you to show why it is true. From the observation of experimental data, it is reasonable to assume or guess that f of nu by t has the following form. Finally, we can write small u of nu t or energy density in the following form. This is what Wien derived in his 1896 paper. Here the constants A and B needed to be calculated experimentally. Later it was found that although his prediction matches with high frequency region pretty accurately, it fails in the low frequency region of the spectrum, as you can see in the figure. This is where Planck enters into the picture. He fixed this problem with an elegant case. German physicist Max Planck, in a series of 5 papers during 1897 to 1899, showed the relation between spectral distribution or the energy density function and the mean energy, capital U, to be this relationship. Here in the energy density function small u d nu, the term 8 pi by c cube nu square d nu tells us the number of Hertzian oscillator, creating a wave of frequency between the range of nu to nu plus d nu. And the term capital U, or the mean energy function, tells us the amount of average energy each of these Hertzian oscillator radiates. Now Planck was aware of Wien's law, so he deduced that the mean energy function capital U to have the following form. Planck was interested in the entropy of this Hertzian oscillator. So to derive the relation between entropy S and mean energy function U, we can start again by the first law of thermodynamics. And by doing some math, we see that ds by du equal to 1 by t. Then he wrote temperature in terms of the mean energy function from this equation and substituted in the equation above to get this relation. By integrating it and considering S vanishes as u becomes 0, we get this relation. If we differentiate this expression twice and with respect to u and take the inverse of it, we get this relation. Let's call it R. But later, due to a discussion with his colleague Rubin, he came to know that Wien's law was not correct for the low frequency range of the spectrum. He also learned that at low frequency, capital U, or the mean energy function, becomes proportional to temperature, or we can say that U is equal to eta t, where eta is just a proportionality constant. Then we can write ds by d nu equal to negative eta by u. If we try to figure out R from this expression, we get R equal to u square by eta. Here Planck made an observation. In low frequency, R is quadratically dependent on u, and in the high frequency region, R is linearly dependent on u. If we add them up together, we see that in the low frequency region, the linear term becomes dominant, and in the high frequency region, the quadratic terms become dominant. Then R must be their summation. If we not take its inverse and integrate it over the boundary condition, then we get this relation. By rearranging this equation a little bit, we finally get this equation. The mean energy is equal to this expression, complicated expression as you can see, Substituting it into the energy density function, we get this relation. To figure out the constant eta and v, we can use some approximation. For low frequency, term b nu by t becomes really small. We can use Taylor expansion for e to the power b nu by t and ignore the higher order terms to get this relation. As we already know that Rayleigh-Jeans law is correct for low frequency, we can compare it with Rayleigh-Jeans law and see that eta is equal to kb, where kb is the Boltzmann constant. Planck has also named a to be h and calculated its value from experimental data. So we can say that b is equal to h by Boltzmann constant. Then the final form of Planck's law and blackbody radiation spectrum is, as you can see in this equation, the relationship between the energy density function and the frequency is related, as you can see in this equation, and the mean energy function is related to frequency, as you can see in this expression. This equation predicts all the theoretical data correctly, but Planck was not satisfied with it. Although his formula predicts all the experimental data, he didn't have any explanation for this formula. In his statement, it was just a lucky guess. So after discovering this result, Planck dedicated himself to finding an explanation for it. After months of endeavor, he managed to find a justification for this equation, but little did he know that this discovery would change physics forever. In this law, the biggest conundrum was the mean energy density function, or the mean energy function capital U of nu t, or frequency range nu to nu plus d nu. Let's imagine again the setup. There are ginormous amount of atoms on the wall of a cavity. Due to heat, they are wiggling with different frequency and different energy. Among all of them, some of them will have a frequency between nu to nu plus d nu, though it's still a huge number. But even though they have the same frequency, they may not have the same energy, since they may have different amplitudes. We need to know their average energy. From Maxwell's energy distribution law, we can calculate the possibility for an atom to have energy epsilon. From Maxwell's energy distribution, we can calculate the possibility for an atom to have energy epsilon, and we can use it to determine the average energy by this equation. Planck decided to study this law in detail because he believed that this is the root of all problems. Ludwig Edward Boltzmann showed an elegant proof of this result in his 1877 seminal. He proved it purely on the basis of statistical argument. He derived it for the case of gas molecules, but the argument can be generalized for a lot of other situations in physics. He imagined a box with a total n number of molecules with random velocity and kinetic energy. Then he divided the total energy E of the system into S pieces and considered n1 molecules to have epsilon 1 and 2 molecules to have epsilon 2 energy, and so on. Then we can say that the summation of ni's is equal to the total number of molecules, n, capital N, and the summation of total energy is equal to capital A. He also considered epsilon I equal to I epsilon, where I is an integer and epsilon is the smallest amount of energy. It was just a math trick which allowed him to perform permutational computation. Then he tried to figure out how many ways can we arrange these n1, n2, n3 ... particles into epsilon 1, epsilon 2, epsilon 3 energies. Let's call it a particular macrostate, and the number of ways we can achieve the macrostate is omega. He computed it permutationally to be this expression. Let's call each of the particular arrangement a microstate. That means for n1, n2, and n3 number of particles, you can arrange them into omega different ways into the energy levels epsilon 1, epsilon 2, and epsilon 3. That means there are omega number of microstates for each of these arrangement of particles or macrostates. If we change any one of these n1, n2, and n3, it will indicate a different macrostate. Now let's assume that the particles inside the box spends an equal amount of time in each of these macrostates, which is reasonable. Now which macrostate has the greatest possibility to be observed? The macrostate with the greatest number of microstate, of course, because in a random process they simply has the greater number of ways to appear. Now if all this math sounds too complicated, then let me explain it to you with a simple analogy. Now we are going to shake this box really hard, and the question is, how many ways we can achieve 0 head or 2 head or 5 head or 6 head or 7 heads? Consider this flower pattern as head. Now let's start the experiment. Now before we start the experiment, let's do the math, or 5 or 6 or 7 heads. If we want to know how many ways we can achieve 0 heads, we can calculate it here as follows. Since there are 15 points, divided by 0 head times 15. If we calculate it, then we are going to get just 4. We get 2 heads. Again 15 divided by 2 factorial. Now let's say how many ways we are going to get just 1 head. 14 is equal to 15 again. Then let's say how many ways we are going to get 2 heads. It's just 15 factorial divided by 2 factorial times. And there's 105 ways. Now, how many ways we can achieve 6 heads, let's say? Sorry. Ways we can achieve 6 heads. Then how many ways we can achieve 7 heads? It is equal to 6,435 ways. Minus 8. And we can go on and calculate, let's say 9 or 10 heads or 11 heads. And as you can see, the number of ways we are going to get 6 heads or 7 heads or 8 heads are way greater than the number of ways we are going to get 0 heads. Well, which makes sense because it is highly unlikely after every shaking we are going to get 0 heads. The possibility of that happening is really low compared to the possibility of getting 7 heads or 8 heads. Let's test out. Here we have got 15 coins. We are going to shake it. As we have already said, we are going to count. We are going to consider this flower pattern as head. We can keep going like this, and most of the time there will be 5, 6 or 7 heads, and the probability of getting 0 head or 1 head is really low compared to getting 5, 6 or 7. So what we learned from this experiment is that after every time we shake the box, we expect to see 6 heads, 7 heads or 8 heads most of the time, since they have simply more number of ways to appear compared to, let's say, 0 heads or 1 head. And which is true in general for any system. We expect to observe the system in a macro state, which simply has the greatest number of microstates. The same happens for the molecules, except instead of heads and tails, we have different values for N1, N2 and N3, or different macrostates. So Boltzmann proposed that the only macrostate we will be able to observe are those for which omega is maximum. That means we need to figure out for which values of N1, N2 and N3 omega is maximum. In short, we need to differentiate it with respect to Ni's and set it equal to 0. To make the function more workable, let's consider logarithm of omega. If omega is maximum, then ln omega is also maximum. Now if we differentiate it and use summation of ni equal to capital N and summation of ni epsilon I equal to capital E as constraints in Lagrange undetermined multiplier method, you will eventually see that ni is proportional to e to the negative epsilon by T. Now it's a lot of work, so I'll skip the math here. That means the probability of a particle having epsilon I energy is given by this expression. Now to calculate the average energy of the particles, all I need to do is use this formula where epsilon bar is the average energy of each of these Hertzian oscillator. Now if we consider epsilon tends to 0 and allow any value for epsilon I, then it becomes a continuous function, and as tends to infinity, then we get the previous equation where summation is replaced by integration. Planck's original idea was to calculate the entropy of each of the Hertzian oscillator. We can easily calculate it by simply integrating this equation here and taking the limit as limit q tends to 0 as equal to 0, and arrive at this equation for entropy. It means the oscillation having a frequency between nu and nu plus d nu has an entropy as shown in the equation. This is a result from his previous formula for which he has no explanation. It was clear to him that classical theory of physics like thermodynamics or the traditional physical law was not going to give him an answer, so he turned to Boltzmann approach of thermodynamics. Although he was not a fan of Boltzmann theory, it was the only choice available to him. He started studying Boltzmann law really deeply. Boltzmann considered a system to be composed of immense amount of tiny atoms or particles. Then he assumed them to have energy composed of a finite number of divisions, epsilon, just so that he can apply permutational computation on them. And after doing all the calculations, he would consider the division of energy to be infinite and epsilon tends to 0. Planck simplified it even further and applied the same treatment for his Hertzian oscillator. He considered that there are a number of particles in total with frequency within nu to nu plus d nu, and the total amount of energy they have to be E inside the cavity. He considered the smallest finite amount of energy to be epsilon and equal to lambda epsilon. Lambda is the integer which is the total number of division of the whole energy. Don't confuse it with the wavelength lambda. He also defined the entropy described by Boltzmann to be as equal to kV ln omega, where omega is the number of microstate of a particular microstate. His argument behind this definition of entropy is that entropy is an additive quantity, since when you mix two separate gases, their entropies are being added, but their microstate are being multiplied. Only logarithmic function shows this kind of property. Then he tried to calculate the total energy of his Hertzian oscillator in the same manner. First, he needed to calculate the number of microstates. In other words, in how many ways can lambda bits of energy arrange themselves in a number of oscillators. By Stars and Bars method, we can calculate it to be this. Then he calculated the entropy to be this equation. By applying Starling's approximation and doing some manipulation, we get the following equation. Substituting the value of lambda, we get this. To get the entropy of each of the Hertzian oscillator, we just need to divide it by n, and E becomes the average or mean energy of the Hertzian oscillators, where U is the average of each of the Hertzian oscillators. Now here, notice that we cannot consider epsilon to be 0 anymore, because if we do that, we see that the oscillators to have infinite entropy. So we are forced to assume that epsilon is some finite amount. We cannot consider it to be arbitrarily small. That means the energy in the cavity is quantized. The total energy is made up of a lot of tiny bits of energy. If we compare it with the previous equation, we see that the smallest bit of energy or quanta epsilon to be equal to h nu. Then Planck realized that this is why he was getting wrong result using classical assumptions, because to calculate the average energy, we had to consider that epsilon tends to 0 to make energy continuous. But as you can see here, we cannot do that anymore. So to figure out the average internal energy, we must use this equation, the summation one, and calculate the sums in that equation, considering epsilon I equal to be I epsilon, where I is equal to 0 to infinity, we get the average energy of the Hertzian oscillator to be this. Substituting epsilon equal to h nu, what we get is exactly the previous equation. The result was so shocking that even Planck himself could not believe what he discovered. Energy is not continuous in nature. Rather, it is composed of a lot of tiny finite bits of energy, what he called quanta. Later, Einstein used this idea of quantization of energy to describe photoelectric effect. Because of this discovery, he was awarded Nobel Prize in 1921. Later, he did some really important theoretical development of quantum physics, based on which Schrödinger, Heisenberg, Paul Dirac developed much of the notions of modern quantum physics. That's it for today. I hope you guys really enjoyed the video. If you like the video, please make sure to subscribe the channel. I will meet you in the next video.